Hello, everybody, in the wide open world. Oh, by the way, proper disclaimer, if you are not comfortable with being recorded, you currently are. Well, I guess your chat is, so leave if you don't like that. But for the purposes of people trying to watch this after the fact, this workshop is being recorded. So, hi, everyone. My name is Eason, and this is normally that would say cybersecurity, but we are being so cryptography oriented that it says cryptography, elliptic curves, and you. Over the course of this 10-hour presentation, we will go over many topics on elliptic curves, such as what is an elliptic curve and what is you. The check-in code for this workshop is crypto, where the 0 has been ingeniously replaced with a 0. So use that at ACM's official membership portal to gain points that are for sure a real currency that have monetary value in the real world. Obligatory statement that this presentation is proudly streamed with the beautiful, amazing platform known as ACM Live. Whoever made this streaming platform sure is a god, and I respect him massively because that is how this workshop is being viewed by all of you right now. And these are the guys who made it. And when I say it, I mean the presentation. In other words, like Cyber and TSE, we made this presentation. We spent a while on it, although I will say that about 80% of the effort happened in the last 20% of the time. That's more my fault. I've been busy. But this is my last big workshop for the quarter, probably, hopefully. So we're going to make it a good one. Let's do it. So just a brief introduction to myself. You may be wondering who this person talking to you from his garage where his desk mysteriously is. Who is he? What gives him the right to talk down to me like this? To which I have many responses. I am a mysterious individual. I have received many comments and concerns over the years, such as can hack, learned Python for this workshop, and Mrs. Papa John's in a sad way. But if none of those answer your question and you still don't know who I am and you're absolutely dying to get it out of me, then all I'll say is that you should take this and interpret it as ASCII, and that is my name. And with me here today is the illustrious David Hacker from Triton Software Engineering. I invite him formally to introduce himself to the audience.
Hello.
We can hear you.
I'm here. Hi, I'm David. That is what I look like. And yeah, there's a lot of information about me on this slide, but I'm not really going to go over all of it. I guess main things to know are that I am TSE's technology person, and I'm a third year undergrad here. And yeah, I like cryptography and elliptic curves.
Don't we all? Okay, good. We're all here for the same reasons. And that is the dynamic duo that is presenting here today. And with introductions out of the way, I would like to talk a little bit about today's quote. Such as the way, with every presentation, I must provide a quote at the beginning of the presentation that embodies the message of this presentation. Today's quote is, "Good crypto is a hacker's worst nightmare. Bad crypto might as well not exist at all." Does anyone in the audience know who has said this clever statement? Yeah, this isn't someone famous. But if you were at my workshop last week, you would know who this is. That guy from last week. Yeah, actually, Eason is right. It is Yifan Liu, who is a very famous hacker, tinkerer, especially in the field of cryptography. He was the mysterious person. I wish I could have a picture to put here, but all I have is this silhouette with a question mark on it. We think he goes to Harvard, but then other than that, no one knows who this guy is. It would make sense that he goes to Harvard because he's really good at making flowcharts. He wrote up the very large 3DS crypto system analysis article that I briefly summarized in my previous workshop, 3DS hacking, which you should go see after this one, because obviously that's what you choose to do with your Wednesdays, is just watch my workshops on repeat. So it's time for introductions. We're actually going to get to the meat of this presentation already. Boom, right out of the gate. We're going to talk about cryptography as a motivation, right? So, and stop me if you've heard this before, right? But say we have a person named Alice, and say we have a person named Bob. Actually, you know what? Hold on. I have a better question. Let's do a poll. You've heard this example 1,000 times, yes or no? Have you heard a cryptography-related example with these characters, Alice and Bob, before? That is the question I am about to ask you. Because chances are, if you have done any cryptography whatsoever, you have heard this motivating example. These dynamic characters. Really, the only people saying no right now should be the ones who haven't done cryptography before. So David, I'm very concerned that you said no. They talk about Alice and Bob all the time in every single crypto class I'm in. That's how they like introduce it. Like the person sending the message is Alice and the person receiving is Bob and the eavesdropper is Eve, and you have to, yeah, I don't know. Names make it easier, I guess. All right, thank you for participating. It looks about 20% of you are seeing this for the first time, but a whopping majority of you, the rest of you, have indeed been subject to this kind of tired Alice and Bob analogy. So to make up for the fact that this is a tired analogy, let's spruce it up a little bit. We're going to throw out these characters, Alice and Bob. We're going to create a new introduction to this topic using completely new characters that I myself have painstakingly developed. Okay, you ready? We're going to put some faces to these names. So here we have Bob. He's a handsome looking fellow. Just looking into his eyes, I know I would trust him with anything. And here we have Alice, a beautiful lady, very feminine. She is a nice person, for sure. Like, these two are a match made in heaven, you can tell. And Bob loves Alice. He's totally got a thing for her. And so he wants to send Alice some secret messages. Well, just messages. It doesn't have to be secret. Like, you just want to talk, you know? But then there's a problem. Yes, that's right. It's already what you're thinking of. The third character in this dynamic trio of individuals. That's right. Alice's dad is waiting there. Alice's dad will not take kindly to just anyone talking to his daughter. Oh, no. He is watching everything you do. He's not going to stop you, right? He doesn't want to be controlling. You can go ahead and talk to Alice, whatever. But you go through me first. I read what you write before you give it to Alice. So no funny business, right? And clearly, Alice and Bob need to use encryption in order to send secret messages to each other successfully to get past Dad's prying eyes. So let's talk a little bit about symmetric encryption, which is the kind of encryption that you guys are probably most intuitively familiar with. Even if you have never dabbled in encryption, you have an understanding of encryption that probably resembles symmetric encryption. So say you have a plain text document, right? And basically you have a key, which is usually a set of ones and zeros, just information, but a very specific key that allows you to transform this plain text into ciphertext. Now, this ciphertext is completely unintelligible to anyone who doesn't have the key. And right? That's symmetric encryption. The defining feature of symmetric and what makes it symmetric is that, hey, look, if I put it like this, these keys are the same key. These keys, the same key that you use to encrypt is the one that you use to decrypt. And there's actually a pretty big problem with this. But we'll go into that later. Basically, how do you go about keeping this key secret from the dad, so to speak, the eavesdropper? Let's just say he's got a degree in mathematics, so he's a smart guy. If he sees you transmit the key, it's over. It's not a matter of not knowing what the algorithm was. He'll figure it out if he can see the key. He's a genius, right? So our goal is to keep it from him in such a way that there is no way, no matter how smart he is, for him to realistically figure out what the key was, and by virtue, what the plain text was, because that's what we really care about. how do we agree, Alice and Bob, both, how do we agree on a key to use without sending the key to each other, right? That's where dad steps in, is when I try to send the key, send anything to Alice, the dad steps in and confiscates it. So how do we agree on these ones and zeros that we're using to encrypt and decrypt without transmitting it over the line? And the answer to that is, who knows, but maybe we could try something other than symmetric encryption. Symmetric encryption implies that there must exist something referred to as asymmetric encryption, where the keys that you use to encrypt and decrypt are not the same key at all. In this context, you use one key for encryption and a different key for decryption. And most importantly, these keys are, it is very difficult to discover one without the other. Or specifically, if you have the encryption key, which is referred to as the public key, it is almost impossible for you to discern what the private key was. No less impossible than it is to just have the ciphertext and try to figure out what the plain text is without the key. What's nice about this is that we actually don't care if dad sees the public key, because all that really lets him do is encrypt things. We only care if he can see what we write. If he can't tell what we wrote, then it's not a big deal. And he can't tell what we wrote without the private key. So we do still need to protect that key. We need to keep that private to ourselves. And that's where the nature public and private comes from. So how can we use this to send secret messages? Well, it's very, very simple. Let's just imagine that we have all of our characters on the stage, and there's Bob over there with his plain text and his private key and his public key. And Alice is off to the other side of the stage, and she actually also has her own, notice they are different keys, she has her own public key and private key pair that is completely different from ours. So we can't, it's not like we generated these keys individually, and we're not trying to like figure out what each other's keys is or anything like that. We have our own sets of keys. The reason why the top of this page says the Diffie-Hellman paper is because this is basically, minus the horrific like mutilations of my senior high school photo, is basically word for word exactly what was originally proposed in a paper in 1976 called the Diffie-Hellman paper by Diffie and Hellman. But we'll talk a little bit more about that paper in a minute. So the first stage of this procedure is Alice gives Bob her public key, but hides her private key. Now, Dad obviously has this public key, which makes perfect sense because Alice had to send me the key somehow. But using this public key, I can now create ciphertext that only Alice's private key can read, but only Alice has Alice's private key. Alice's dad does not have Alice's private key. So when I send the ciphertext over, yes, Alice's dad ends up with a copy of both Alice's public key and the ciphertext, but that doesn't help him at all for figuring out what the plain text is or for figuring out what the private key is. And so Alice can decode her message using the private key. And when she reads it, she is, of course, infatuated instantly and wants to reply as soon as possible. Alice's dad, on the other hand, does not have enough information to figure out what was sent. And somehow, despite these two parties never having met before, they have managed to send information. And of course, the reason why we have our own pair of private and public keys is that Alice uses Bob's public key to reply, and then Bob decrypts it using his private key. It's basically a two-way thing. But both parties have to have private keys and public keys. So the Diffie-Hellman paper was originally proposed as a theory in 1976 because the paper actually lacked a practical implementation. That's what made this paper so substantial, is they came up with this concept of asymmetric encryption and public key cryptography, but they didn't actually have a candidate mathematical function that had all the properties that are necessary for this public key, private key system to work, right? Because those are just ones and zeros. There's some algorithm that determines how this stuff is encrypted. Specifically, the terminology they used was they needed a trapdoor function, which is a mathematical function that is difficult. And when we say difficult, we mean feasibly impossible. That is difficult to undo unless you have additional information, such as the private key. And the private key makes it trivial. and that's the trapdoor part is, oh, there's a trapdoor letting you go backwards in this function, but only if you have the private key. So time for a poll real fast. This is going to be a quick refresher on some public key stuff. Which one of these constitutes a mathematical trapdoor? I'm actually going to go ahead and announce the options here, but I'm going to let David talk about the results after this. So we have a few options for what types of functions. And if you have no idea, it's fine. This is just us polling to see what the comprehension is in this particular audience. Say option A is prime integer factorization. Option B is the discrete logarithm, whatever that is. Option C is lattice problems, whatever that is. And option D is all of the above. So I'm going to go ahead and open up the polls for a couple of seconds. And you guys can vote at your leisure. And I'm going to read chat for a little bit. Is my mic cutting out at all? One of you mentioned it in the chat. I wasn't sure. Okay. I'll get a little closer to my mic. I know I'm kind of like meandering away from my desk. It's unusual for me to have this much room when I'm presenting. All right. Let me take a quick look at the results of the poll. We're actually pretty divided. So we had a lot of, and you guys can't see the results, so I have to tell you, but about 20% of you said what I believe constitutes the correct answer, which is D. But an overwhelming amount of you are familiar with A, prime integer factorization, which is, of course, used in RSA encryption. But I'll go ahead and let David talk a little bit about that one. If that's
okay, so about prime integer factorization, well, I guess, yeah, like Aaron said, I'd consider all of the above to be correct, but as for integer factorization specifically, basically prime integer factorization is the problem. You're given a composite number C that equals P times Q, and P and Q are both very, very, very large prime numbers, usually in the thousands of bits. So like, I think most RSA key sizes are around 2048 bits. So your prime numbers are going to be around that size. So regardless, it's very hard to actually compute the factorization of this composite number. There's a lot of advances recently in the mathematical world that have tried to make this faster. The most recent advance was the general prime number sieve in like the 1990s, and future or current improvements have just been like incremental changes built on top of the general number sieve. But yeah. So the next, like Aaron said, the discrete logarithm problem is also a mathematical trapdoor, but it's sort of a more uncommon trapdoor. I wouldn't say it's uncommon, but it's certainly less well known. Basically, the discrete logarithm problem asks if you have the equation b to the power of x equals a, where x is usually some integer and b and a are like elements in what's called a mathematical group. We'll get into that later. It's very hard to compute what x is given a and b. And elliptic curves use this, which is why we're going to talk a whole lot about the discrete logarithm problem. There's also a crypto system called LGAML, which also deals with the discrete logarithm problem. And technically, the discrete logarithm problem and prime integer factorization are trapdoors given the current state of computing, but as soon as quantum computers become viable, then both of these trapdoors will become very much broken. So that's why we have lattice problems to the rescue. So lattice problems are currently thought to be infeasible even for quantum computers. There exist no algorithms to compute these types of problems. Lattice problems are a bit hard to explain, but basically they deal with lattices, which are essentially points uniformly spaced out via some choice of a vector over some huge multi-dimensional field. And basically, given some point interspaced between these lattice points, you have to find like the shortest vector to one of the lattice points. You just look it up on Wikipedia. It's a bit complicated to explain, but there exist a couple of crypto systems that make use of this. New Hope is one of them, which I think Google has actually rolled out. RLWE stands for Ring Learning with Errors. It's also another good post-quantum crypto system, and NTRU is also based off of lattices. Aaron, I think you're muted.
I have to unmute myself apparently if I want to be heard. That's so weird. I don't know whoever designed this ACM Live thing. Honestly, I bet he's stupid, because that's such a bad feature, muting. Anyways, thank you very much, David. As you heard from that little spiel, all of these have cryptographical implementations based on the fact that they are mathematical trapdoors. So the answer is, of course, D. Next up, we have something. If I refocus this window, there we go. We're going to talk a little bit about elliptic curves since we said we would. I think we're like 20 slides in technically, but yeah, it's this. I thought elliptic curves was really scary, but turns out it's just this. Like it's not anything else. It's this curve exactly. That is the equation of this curve. It makes a cool shape, kind of like a parabola. I mean, it's not that different from a parabola, really. Depending on what A and B are, you can have all kinds of different looking curves, as illustrated in the grid of different forms below. Your A is kind of like a parameter that you can tweak. B is the coefficient of the third term, which is constant. And M is your modulus, which isn't in the equation, but we will talk about modulus in the future. But these three things are the things that you adjust in order to create an elliptic curve that you are going to use for cryptographic reasons. Your A, your B, and your M, your modulus. So I would like to put this in your hands so you can kind of get a feel for this. Go ahead, run on down to acmurl.com/hotcurves and mess around with an elliptic curve graph that I created on Desmos. And you can tweak parameters and stuff. And also it supports showing off point addition, but we're going to talk about point addition later. I'm going to go ahead and open this in my browser as well as post it in the chat. Let's go ahead and do https acmurl.com/hotcurves. I'm also going to put it in the shared notes so that anyone who comes by later has access to it. And I'm also, thirdly, I will open it in my browser so that you guys can see it. This is what it looks like. You're free to tweak this in your own browser, but as you can see, the red line here is a curve, and this black line will be important later. Don't worry about the points P, Q, and R, and negative R. Don't worry about any of that. What you have over here, though, are sliders for both A and B, so you can go ahead and drag these to see how the shape of the curve changes. A and B have different effects. It almost seems like A kind of like decreasing A causes the bulge, so to speak, in the curve to distend somewhat, whereas B kind of like shrinks the width of it almost. That's one not really intuitive way to think about it, but that's a way to think about it. You can also drag around these points, Q and P and R. I'm not going to talk too much about it since basically what it's illustrating is point addition, which is obviously the key part of elliptic curve cryptography. What's important to realize is that a property of this curve is that if you draw a line through any 2 points anywhere on the curve, you will necessarily intersect with the curve in 3 points, unless you are exactly tangent to the line with your intersections. But if you go through this curve at any point twice, you will necessarily go through this curve 3 times. That's twice without being tangent, because obviously if you're tangent, you can, like I can move P and R together until they're basically touching, and then I'm tangent-ish, right? And that's 2 points. But without being tangent, you necessarily have to get 3 points no matter what. So that's cool. That is a very useful property. What it means is that points on this curve might be what we can call a mathematical group, but we will talk about that in but a moment. We're going to go back now because I just wanted to briefly detour into that demonstration. Let's talk about groups. Don't worry, this is an abstract algebra concept, but I'm not going to get into it in like a very rigorous way. We're just kind of going to gloss over it and talk about properties of it. And also, don't worry, when I say groups, I mean you're not going to have to like get into a group. I'm not going to start up breakup rooms or anything like that. Don't worry, this is in your Zoom lectures. It's fine, breathe. But a group is a mathematical construct. Specifically, it is a set of elements. They could be numbers, they could be vectors, they could be points on an elliptic curve with a closed operation. And the adjective closed has a rigorous definition in mathematics. It means that when you take 2 things and add them together, or whatever this operation is, it could be addition or multiplication, you get another thing from the original set. That is what constitutes a group, that kind of set of elements, closed operation, pairing together is a group. So for example, integers and addition. Any 2 integers you add together, you're going to get another integer. And every integer has an inverse. If I have 3, I know that I can add -3 to it to get back to 0, right? Everything has an inverse. And 0 is its own inverse, so to speak. So integers and addition are groups. Vectors and addition, you just add each component of the vectors, and that also constitutes a group. Both are closed because, again, they take 2 elements from our original set, the integers or the vectors, and produce another element from the set. So it's time for another poll. Which of these is a group? Just based on the things I've talked about so far, let's see what you guys think about these options. So we have addition over integers, which we just talked about, multiplication over integers, multiplication over rationals, and all of the above, or all but one of the above. So I'm going to go ahead and open up the poll, and you guys can tell me what you think. Try not to go too crazy with your SAT score taking skills. Let me know what you think. And I'm also going to look at the chat. We are getting abstract, Kyle, but fortunately, this is still pretty easy to comprehend for a lot of people, I feel. So we have some, actually, never mind, we're split. We're split. I'm excited. Neck and neck, neck and neck. Okay, so technically, so we're basically evenly split between D and E, which is all of the above or all of but one of the above. So let's talk about that for a second, actually. Let's do this. So let's talk about each of these in order. So for addition over the integers, I'm likely to say yes, because we just used that as a motivating example. Every integer has an additive inverse, which is part of being closed. Multiplication over the integers is not, however, because think about it. 1/2 is the inverse of 2 as far as multiplication is concerned, but 1/2 isn't an integer. But that means that the operation isn't closed. In other words, if I have a 2, there's nothing in the integers I can multiply that by to get 1, which is the unit of the group, so to speak. So In this case, 1/2 is the inverse of 2, which leads me to the second point, which is if you extend the integers to the rationals, multiplication is a group operation. In fact, you can even say something as daring as this, which is the rationals are the integers with multiplicative inverses added in. That's literally what they are. So yeah, that's cool. And then that leads to the natural conclusion that all but one of the above is, of course, a group. So thank you very much for playing, guys. Let's talk a little bit about elliptic curve addition, which I mentioned earlier. So let's try to turn this into a group, these points on this curve. If our set is points on the curve, can we create an intuitive way to add points together to get another point on the curve? And this has a lot to do with the property that I talked about earlier, but of course the answer is yes, you can. And in fact, it satisfies all of the properties of a group. And the definition that we made as humans to make this work is as follows. Basically, if you want to add 2 points on the curve together, you draw a line through them, right? And because of what I said earlier, no matter what, if you draw a line through 2 points on the curve, you will necessarily intersect with the curve a third time. That third time is the point. That is the sum of those 2 points. However, I feel like I also have to say that there is a very good reason why we do this, but we don't just use the point that it intersects with. We actually flip it back down onto like over the x-axis to get the negative of that, and that is the true sum. There are basically, that's to keep it from like growing exponentially and just like going off into infinity, and it kind of keeps it controlled, kind of keeps it centered around the heart of the curve, so to speak. You'll also notice this diagram points out that there is a special case when the line is tangent. You just, or excuse me, when your 2 points are the same, that is a tangent line, and where it intersects with the curve the second time is the sum of that point with itself. So we take that special case of the line being tangent and call that's basically doubling a point, adding a point to itself, p plus p. So yeah, that is the addition law. It covers basically all the cases except I'm kind of glossing over a few details, but I think it's kind of intuitive. So what about this modulus that I mentioned a while ago, but haven't like talked about too much? Some of us might be familiar with this modular arithmetic business, but for those of us who are not, this will be a little bit of a rundown. Performing elliptic curve point addition without a modulus means that we could potentially need unlimited storage to hold our points, right? Even with the fact that we flip over the x-axis to keep the points relatively small, we're still going to grow in size or end up somewhere that is, for computing purposes, close to infinity, and we have to store those points somehow. So instead, we use a modulus to limit the growth of our calculations and keep things calculatable and fast. If we use an n-bit modulus, an elliptic curve point will always fit in 2 n bits of memory, right? The x-coordinate and the y-coordinate. Although with one, you could find the other. In fact, security assumptions will not hold if we are not over a proper multiplicative group. So there are security reasons as well as storage reasons for why we are using a modulus. And this bit is, I believe, a screenshot from the algorithm or the formula that follows as a result of the algorithm we talked about earlier. This is the formula that calculates R. So it actually isn't that complicated. If you look at it, it is not that complicated of a function. You could definitely write that code without much difficulty, hint, hint. These calculations, by the way, are all done under a modulus of m. So that means after every integer addition, integer subtraction, or multiplication, we take the mod m, which we haven't really talked about what that is yet. But for those of you who know, we take the mod m at those steps. So time for a poll or a hazing. I don't know. It kind of depends on your interpretation. The poll is simple. All right. What is 6 plus 9? Here are your options. A, 1. Or it could be B, 2. Or It could be C, 3. And finally, it could be D, 4. I'm going to go ahead and open up the polling, and you guys can tell me what you think about this. No, those are your 4 options, guys. Good luck. Good luck, my friends. Ooh, we have a lot of uncertain people. They're taking their times voting. Not very many people are entirely sure what to put here. Oh my goodness. So, some of you, most of you, all of you have responded by now. So, this is kind of an interesting result. I'm going to go ahead and take a picture of it and show it to you guys because I feel like it's worth you guys seeing this. Let me quickly, boop. There it is. As you can see, C is the popular answer. A is also an answer that multiple people picked, and people weren't really a fan of B or D. I'm not entirely sure what all of your justifications were, but let's talk a little bit about C, because C is the correct answer. For those of us who are rightfully still confused, this is an unfair question, to be clear. I'm purposefully hazing you right now. Here is perhaps a hint that will, because you yourself in the audience have done this calculation before. I'd be willing to bet you have done this calculation dozens of times. Here is a hint. We've all done this, right? We've all had to calculate, okay, if I go to sleep now, how much time am I going to have? Or if I sleep on the flight, how much time am I going to have? Oh, but, we go around the clock, so 6 plus 9 is equal to 3. If I want to sleep 9 hours and I go to sleep at 6, I got to wake up at 3, which I would never do that because going to sleep at 6 is for, my grandparents. Anyways, there you go. Now, I'll again admit that this question isn't really fair. If I wanted to make this question fair, I would have added this bit, right? This is the notation that we use to indicate that our calculations aren't happening on the normal number line. They're happening on the mod 12 number line, the mod 12 universe. We put it in parentheses to kind of indicate it as an afterthought. By the way, this is the context. We're doing this on a clock. That's mod 12, so on and so forth. So let's talk a little bit about modular arithmetic, kind of a deep dive of what you can think about it conceptually. So basically, for our purposes, it is a way to restrict the size of numbers without losing the ability to do operations on them. So modular arithmetic still has all of the properties of groups, which still allows us to be secure without needing to have numbers that go into infinity. By restricting the size of it, we still have all the operations we need to implement a mathematical trapdoor, even if our numbers aren't capable of getting that big. Although in the case of RSA, you're talking about a prime modulus that's 2048 bits. So it's a big number already, but trust me, it'd be a lot worse if we did not have these modulus stuff going on in the background. Here's one of my favorite ways to visualize this that if I could, I would literally kill every single number theory professor I've ever had for them not showing me this, because it makes a lot more sense for me this way. Here's the number line. This is the integers, or at least the integers starting at 0. Here is the mod 7 universe. The number line is the same size, air quotes. It still just goes off to the right infinitely. The difference is that the first one is the integers, the second one is the mod 7 universe. Notice how in the mod 7 universe, there are infinitely many values, but there are only 7 possible numbers. What we're saying really is that there are an infinite number of numbers that are integers that correspond with the mod 7 number 0. 0, but also 7, but also 14, so on and so forth, in multiples of 14. So you can kind of imagine what the properties would be like, but you can still add things together in this mod universe, and you're still going to end up moving on the number line to where you need to go without losing information. So here's an important caveat. If the mod is prime, this set of numbers is still a group. If the mod is not prime, this set of numbers is not a group. And I won't be able to justify that right now, but just know that it is a fact. So not every modulus will produce a group such that every number has an inverse. But if your number is prime, if your mod is prime, you have a guarantee that every number in your universe has an inverse. So even though you're working on integers, keep in mind, you're not even talking about rationals, just integers. Everything has a multiplicative inverse if you are mod a prime. I will talk about that in a minute. Actually, I will talk about it right now because I have a little bit of a demonstration. This one shows you a graph of a discrete elliptic curve. So not the infinitely many points along the curve, but the finitely many discrete points on this curve against a prime modulus, which again restricts it. So I'm going to go ahead and put this link in chat. In the set of integers in 7 as the mod, what are the multiplicative inverses? Great question. I'm going to demonstrate that very, very shortly. I hope you can be a little patient with me. I just wanted to get this demonstration out of the way, this little exercise. But believe it or not, everything has an inverse. And I'm going to put this in the shared notes as well. And then finally, I'm going to open it in my browser. Here we go. Ta-da! So this is an elliptic curve. Now you might be saying, Aaron, that doesn't look like an elliptic curve. This is an elliptic curve. This nice, curvy thing. This is also an elliptic curve. It just happens to be mod, in this case 13 is the modulus that they load this page with. In actuality, I can make this curve mod anything I want. Desmos actually does support that, but it's going to look kind of weird. Let's do mod a prime number, so like 13, and we're going to square it because technically it's y squared. Anyways, what you get is instead of the curve expanding into infinite space, you get every x value is associated with a value on this curve somewhere. You have the size of the numbers, which is on the y-axis, can get infinitely huge, but you're still kind of constrained to this finite space, and point addition still works and stuff. Obviously, this demonstration that I'm using is not going to work after I mod it because I would have to account for that and everything else. But just imagine this is now the space that the elliptic curve occupies. Now imagine we are only graphing points on these lines that happen to be whole numbers, whole integers. Yeah, it could look like that. I mean, it's symmetrical, right? That's really the only pattern here. If I up this to something huge, like 109, we get what looks kind of like just random dots strewn about. And in fact, there is such a thing as a random number generator that uses elliptic curves. We will be talking about a very famous example later in this workshop. But if you look here, every single one of these points is 2 integers as a pair. And in fact, they even give you the multiplication table for it, or I guess the addition table. If you add the point 581 to the point 853, in this modular arithmetic world, you're going to get this other point out. And you'll notice that this table is complete. Every possible addition produces a number, and every number has an inverse. There are only a few rare examples where 2 points will combine to create infinity, which is actually these are the inverses. So along the center of this column, I believe these are the inverses. I could be wrong. I think I might be wrong about that. I don't remember. 0 is its own inverse. 528 and 581 is its own inverse. That might be true. I don't actually remember. But you could think of the infinity point as like the 1 in multiplication. That's the unit of this group. But understanding that isn't important for getting anything that we're about to talk about. So let's go back. Let's back away from elliptic curves for a second. Actually, let's just leave this open. Let's go back to the presentation. I want to give an example like the one that Thomas was asking about. So we never really defined what it means to be a multiplicative inverse mod a number. Addition, right, is clearly a group on integers that is mod p, right? So turning integers into integers mod some prime number does not affect the fact that addition is a group operation. It's still a group operation afterwards. The question is, what about multiplication? We talked about how because it's not the rationals, it doesn't work. But in actuality, when you're talking about the mod integers, you are capable of taking the inverse of numbers mathematically. For example, what is the inverse of 3 mod 7? Well, here is the mathematical definition of what it means to be a multiplicative inverse in the mod n universe. From, actually, no, this isn't Wikipedia, I wrote this. If A and B multiply such that they are congruent to 1 in the mod n universe, given A, B is referred to as the multiplicative inverse of A, and A is the multiplicative inverse of B. And we also sometimes notate this as A to the negative first to indicate it's an inverse of itself. So based on this definition, do we have any educated guesses on what the inverse of 3 mod 7 is? What can I multiply 3 by to get 1 in the mod 7 universe? Do we have any ideas in the chat? 12 is not in the mod 7 universe, unfortunately. Ooh, Glenn says 5. I actually agree with 5. Wait, I wasn't supposed to agree with 5. Dang it! I was supposed to wait, but yes, the answer is it's 5. And if you wanted to see the math behind that, sure enough, 3 times 5 is equal to 15, which if you were to divide it by 7, you would have 14 divided by 7 equals 2, remainder 1 to get to 15. That's what it means to be congruent. 2.5 does not work because 2.5 is not an integer. Yes, 2.5 is not in the integer universe, let alone the integer mod some number universe. So we will see this written both ways, where 3 times 5 is congruent to 1. We will also see that 5 is the multiplicative inverse of 3 in the mod 7 universe. We'll see it written both ways. So it is time for your first challenge. This is the interactive part. And no, I'm not talking about a poll. You, yes, you in the audience get to do a thing. The goal of this thing is to write a function to calculate the multiplicative inverse of a number modulo a prime. Yes, Chris, even you. You have 5 minutes to do it. Oh, and I'm not saying you have to like go out and just pick the language of your choice and do this. We actually have a REPL for you. Yes, we're taking lessons from hack.py. I invite you all, anyone who's sitting at their laptop and is willing to try, even if you don't have Python experience, to go to acmurl.com/cryptorepl. It should be an invitation link. It may require you to sign up for REPL, which is quick and easy. Just put your UCSD email. You know, I know you don't check that anyways. And then let me make sure I send this link correctly. And once you do, there are 3 different activities or assignments inside of that REPL. I want you to do the one called inverse mod prime. So let me do that in the shared notes as well. Assignments. There we go. And then let me bold that. Ta-da. Also, huge shout out to David for working very hard on a lot of these assignments while I was working on the slides. We did a really good job collaborating and splitting the workload there. So if you go to that URL, you're going to see something that looks kind of like this. I want you to, once you sign in and everything, I want you to go to inverse mod prime. I don't think I wrote a solution. Okay, I didn't write a solution. Whew. And you're going to get this. Main.py over here is where all your code is going to go. There's some starter code for you. And over here on the right is everything you need to know in order to do this assignment. So you have the definition of multiplicative inverse, you have instructions on what to do, some definitions of what everything over here is. So basically, everything I'm highlighting right now is stuff that's given to you. This is the scaffold of your function, inverse mod prime. And I want you to make the definition of this function return the modular multiplicative inverse of a number only when the modulus is prime by using Fermat's little theorem. So you don't have to worry about the number not being prime. It will be prime. That's the guarantee I'm giving you. So Fermat's little theorem is a very easy way to do this with prime numbers using this identity. I'm going to go ahead and let you guys kind of mess around with that identity a little bit and see if you can come out with any ways to calculate a to the negative 1. Note that if you end up doing the Fermat's little theorem method of implementing this, you will want to use the function that I have provided for you called palmod. All that does is it takes the power of a number to a certain to a certain power very, very efficiently, mod a number. So it just raises something to a power in the mod universe, the mod that you indicate. So you pass in the base, you pass in the power, and you pass in the mod. That's it. Don't worry about accumulate. It's just set for you. Or if 5 minutes is too much time for you, go ahead and do the extended Euclidean algorithm version of this, which works on all numbers, not just prime numbers. Good luck with that, though. It's kind of a pain. So instead, I've given you some basic information about what to do in those cases and some reference articles that may help you. But go ahead and take 5 minutes. I'm going to go ahead and pause recording unless someone has questions. The Fermat in Fermat. Fermat? I think you mean Fermat. Fermat little theorem. All right, I'm going to pause recording for a little bit since no one has important questions at the moment. Welcome back, everyone. I'm going to briefly talk about the correct objectively response to this question. Not really, there were two options. Just 5 minutes is not really enough time to implement extended Euclidean. Did anyone in the audience happen to try extended Euclidean algorithm in the very small amount of time I gave you guys? Hopefully not. How about this? Let's go ahead and take a poll. Go ahead and say yes if you managed to get the test to pass, and no if you did not, regardless of how you did it, Fermat's little theorem or extended Euclidean or whatever. Okay. Looks like we might have some people racing to get it finished. This one is kind of just a warm-up, so I'm not that invested in you guys getting it just like right out of the gate. I just kind of wanted to introduce this format to you. We're going to do a couple of more interesting challenges of this variety. Looks like we had a couple of people. I'm going to go ahead and take the fact that a lot of people haven't responded to mean that I really pressed them for time and they need a little bit more time to work on it, which is perfectly fine. I agree with that. I'll go ahead and speed things up, though, a little bit and show you something that I came up with. The pseudocode on the Wikipedia article is very helpful. Oh, for Euclidean algorithm? Yeah. Probably Fermat's little theorem, too. I don't know if they talk about using it this way. So with Fermat's little theorem, I really can't think of a better way to do this. So I'm going to go ahead and just say that a to the p is equivalent to a mod, and I'm not really sure if the syntax on that is correct, but mod a number, in this case prime. Oh, fudge. Okay, that's not how to do it. I guess I could just enclose it in a text tag. I'm literally live typing LaTeX here for you guys as part of the solution. All right, there you go. So that is Fermat's little theorem. Yeah, word text. Well, no, it's not a plugin. It's actually just built in. So here is Fermat's little theorem. What we want necessarily is a to the negative 1. Wouldn't you agree? That's what we're trying to calculate. So a better question is, let's just assume for the moment that I have managed to somehow get a to the negative 1, which I have to enclose in curly braces in order to get it to format correctly, on the left-hand side of the equivalence bar. What would necessarily need to be on the right-hand side? Does anyone know? Oh, goodness. Well, kind of as a demonstration, if I do p minus 1, then what's over here isn't a, it's a times a to the negative 1. This is clearly the best way to be doing this. There's no more efficient way, right? So that's just equal to 1. That's true. So what if I did that again? What if I multiplied both sides by a to the negative 1 again? Because this cancels out, right? This creates 1. And then if I multiply both sides by a to the negative 1 again, what we're going to get necessarily is p minus 2 is equivalent to a times, raised to the negative 1, text mod space p. All right, there you go. So that's pretty cool. Yeah, the mod didn't render. It's not one-to-one LaTeX like standard compliant, so I have to kind of make up things as I go. My point is that I have managed to successively get a to the negative 1 to appear there. Apparently, it's just equal to a to the p minus 2, so where p is the modulus itself. And this only works, again, if p is prime, which it is. So given that we have a function here that calculates things to powers, we could just write pow mod, where the first parameter is the base, which is a, which is num in our case, right? And the mod, or the power is, of course, just mod minus 2, according to that formula. And then the mod is just mod. And if I go ahead and run, like I don't have any syntax errors, if I run tests, I adhere to all 3 tests. We can actually demonstrate this too. So let's go ahead and print the result of inverse mod prime when I pass it the motivating example, which was what is the inverse of 5, or excuse me, what is the inverse of 3 when I'm in the mod 7 universe. It will tell me that I have made a syntax error, but it will also tell me 5. So that's cool. I'm not sure why it's giving me that other error. But the point is it works. And if I give it 5, I should get 3. And I do. So that's cool. Great. Congratulations. Let me submit this assignment so I can get points for it because my grade in this class sucks. And then we are going to do another exercise. Boom! I'm going to go ahead and let David take over this challenge and some of the remaining slides. So David, do you want to step in?
Sure, yeah. Okay. The next step is to implement the point addition assignment challenge thing. So that should just be right above the inverse mod prime. Again, everything should be listed on the actual README blurb thingy. It should basically tell you exactly how to go about it. And one of the cool things with Python is actually Python's integers are variable sized because for some reason they decide to put them on the heap. But because they're variable sized, we can support essentially arbitrarily sized numbers, which means that no matter what additions you do, you'll technically never run out of space as long as you still have memory on your computer. But the modulus helps alleviate that problem. Anyways, give it a whirl, and I'll be around and check in 5 minutes. Same with Aaron.
All right, so I went ahead and hit resume recording. David, did you want to show off the solution, or how did you want to do that?
Sure, I can do that. I can switch to the presenter, I guess.
Yeah. Oh, there's all the polls. That's where they go.
Can you see my screen, or do you have to?
Yeah, you have to start the screen share thing and give it permission and do a bunch of other stuff.
All right, how's this?
It started for me and then it ended for me instantly. I don't know how anyone else sees it.
Failed. All right. Let me try switching my browser then.
Sure. Are you using Firefox?
Firefox, yeah.
Really? I find that Firefox works for me pretty consistently, but.
Oh, really?
Yeah.
Okay, let me switch then.
Hey, Ishan, I see you got it. Man, calling you out. Yeah, sometimes you can get caught in like the order of operations of things. Again, much easier if you've been keeping up with the Python stuff. David, I still can't see your screen. Uh-oh. Oh, I think David rejoined as a non-presenter. So let me go ahead and promote him. So David, you're going to have to hit the audio button at the bottom twice to disconnect your audio and then reconnect it with your microphone. You have to connect it with your microphone now that I've made you mod. You should have a button. Okay, you got it. I see you got it. Waiting. Hey, there you go. Your mic is back. Welcome.
Hello. Okay, let me try sharing my screen again.
Yeah.
Okay, are we good?
Mm-hmm. Okay. I see the spinny wheel. Okay, now I can see it. Perfect. We're good.
All right. Actually, let me stop sharing my screen temporarily so I can log in on Chrome.
Hey, okay. I think I see another submission, but whoever you are didn't put your name, so I don't know who you are. Based on the list of people here, I'm going to go ahead and say, guess it's trash. Oh, is it not? Like, someone put like 2 periods as their name. So, okay. You put your name, Jessica. No, you got it, Jessica. I'm talking about the second assignment. Yeah, anytime, Bryce. I'll see you around. Have a good rest of your day. Yeah, later, trash. I call you that with nothing but positive intentions. Oh, did David get locked out again? Okay. Yeah, let's do promote. There we go. You're going to have to disconnect and reconnect your audio again. There you go. And I'll be there. Oh,
all right.
hey,
Am I good now?
Yeah,
Okay.
you're good. I can hear you.
Yeah, so I think last time, so okay, my computer's been having some issues, so hopefully this doesn't persist. Otherwise, you might have to do the screen sharing because my thing is kind of okay.
No worries, no worries.
Let me get to the REPL first.
Good thing.
Okay. All right, are we good?
Let me check. Yes, I can see your screen. Perfect.
Okay, great. Okay, so the solution basically looks something like this. So the reason why I specified 3 parameters is because really that's all there is. There's just 3 parameters required. The first one to look at is this lambda term over here. So this lambda term is actually the slope of the line that Aaron was showing earlier. So if you remember the 2 points, when you calculate a line between them, that line has some sort of slope, and that slope is equal to the lambda. The only problem is that we are performing division over a modulus, which means that we can't just divide these 2 terms together using regular old addition, integer addition, or float addition. So instead, what we do is we convert the denominator into its multiplicative inverse and then multiply that with the numerator. So if you can see here, qx minus px is the denominator here, and that is turned into its multiplicative modular inverse. So now we can just multiply that, which essentially makes it like 1 over the denominator, and then that's multiplied with the numerator, and you get your answer then. So that gives you a number for lambda. We could take modulus prime here, but that's not really an issue. That really only matters for the actual return point coordinates, so we can kind of ignore that for now. But normally you would if you were concerned about space. And then to calculate Rx and Ry, it's basically just plugging in this formula. So like you square the lambda, you subtract px and qx, and then you take the modulus via the prime, and then you return that. So 3 pretty succinct lines. And yeah, of course that doesn't actually get into the whole math behind why you do all this, but it's pretty simplistic. And actually, the cool thing about this is that even though it's so simplistic, it works for basically all elliptic curves. And in fact, in the test cases, if you'll notice, if you run the test, you'll see there's a curve P256. This is actually a NIST standardized curve, and we just give you 2 points on the curve and add them together. And you actually get a 256-bit long elliptic curve point via just this like simple math stuff. So yeah, very Python-esque. Okay, let me go back to. So I guess. Do we want to continue with the slides or that?
Yeah, that'd be a good idea. Let me just share the right screen here. And that was the end of the second challenge. I think after this, there was a little bit of verbiage, but I believe you're in charge of it.
Okay, elliptic curve point multiplication. So this is going to be the next phase. Elliptic curve point multiplication is actually pretty simplistic when you think about it. Basically, if you have an integer n and a point p, you just want to add p to itself n times. Hence, you're multiplying, pn times. It's exactly what it sounds like. So a naive way to do this is just to say q is equal to 0, and let's just add our point to q n times. So just add, and eventually we'll get q. The problem is, what if n is huge? So if you go back to the NIST curve example, the modulus can range anywhere from, n can usually range anywhere from 2 all the way to 2 to the power of 256, which is a very large number. It's well over a quintillion. So if you had to add q to 0, or p to q a quintillion times, it's going to take forever, and you're going to get nowhere. So there are faster ways of doing it. And the preferred way of doing this is a method called double and add. So basically, if you remember the multiply and square algorithm from TSE 21, basically it's the exact same thing. So if you take n, if n is odd, then you compute, you just add p to the recursive call with n minus 1. So you compute p times n minus 1, you do that recursively, and then you add p to it. And then if n is even, we can optimize this case. So basically, we call the function recursively, we get a point back, so p times n divided by 2 is the recursive call. And we have q, and we could actually multiply q. We could use a special operation called point doubling. We didn't really cover this in the addition case, but Aaron talked about it, where it's like if you're adding a point to itself, you don't want to necessarily find the slope between the 2 points. You want to find the tangent slope of the curve at the given point. So we can essentially divide n by 2 and do all of that computation with one doubling operation. So if you look at the master's theorem, it basically says it's logarithmic time. Spare you the trouble of actually applying the master's theorem, but yeah, and that's that snippet listed on the previous slide is also in the README for the next assignment, but we'll cover that. So the third challenge is implementing multiplication using double and add. We give you the double and add functions, and they should be fast and complete. They use all of the previous stuff that we talked about. And yeah, this might be a bit more challenging because it involves more lines, but I think the Wikipedia article is a good source for this. And another hint is that in order to calculate PowMod from the previous assignments, we're using a multiply and square algorithm. So if you look at that multiply and square algorithm, it's basically the elliptic curve point multiplication is just a variation of multiply and square just applied to elliptic curve points. All of the actual structure is the same, from the recursion to all the different cases you have to handle. So that would be a good starting place to look at, besides the Wikipedia provided pseudocode.
Sweet. All right, let's do it. Let's let them go at it for 10 minutes or so and check in and see where they are at. Should look like this, by the way. The parts you have to implement, they give you a little bit of framework. But just make sure you follow the instructions over here, and you'll get there in no time. I'm going to go ahead and pause the recording for a second.
So, like the operations that you do, your implementation doesn't reveal any data about your scalar value. The Montgomery ladder actually only works for certain types of curves. The test cases that we've written actually work with the Montgomery ladder, but they don't actually work for all elliptic curves. So that is another thing to keep in mind. Yeah, same runtime, logarithmic. Okay, talking about the elliptic curve discrete logarithm problem. So the basic idea is you have points P and Q, and you have a relationship such that point Q equals P added to itself n times. So Q equals n times P. And your goal is to find n given P and Q. And this is very, very, very hard to do. There are no known ways of doing this other than basically trying out every value of n. And if you choose your modulus such that it's like a huge number, they essentially have to try every value all the way from 2 to the modulus. So if you have a huge curve like 2 to the power of 256 as your modulus, then it's basically computationally infeasible. And this is why it's a trapdoor function, because it's infeasible. You can't compute n given Q and P. And another thing is that before we've been using like a wide variety of what A, B, and M can be. In fact, for the simple curves, it doesn't really matter what we choose A, B, and M, as long as they like get across the point that you could like add and multiply stuff together. It doesn't really matter what they are. But in actual real world implementation, A, B, and M is very, very important. It's very tied. The curves parameters are very much tied to the security of your cryptographic operations. So that's a special form of a curve is called a Montgomery curve, which looks slightly different from a regular elliptic curve because it has an x squared parameter in it. But Montgomery curves are very fast and very secure. People use very well-known curves. NIST has standardized a couple of them, although they may be broken now. X25519 is a Montgomery curve that is probably the best elliptic curve out there right now. It's the fastest curve currently known, and it's also one of the most secure. And it's used in a lot of places, such as in your browser. But there's a bunch of choices, and that website lists a few of them. So the main reason for using elliptic curves, other than because there's like a bunch of crypto systems out there. So if you have a 228-bit RSA key, it actually doesn't take very long to crack it. So you can, if you ran your computer for a few hours, maybe you could get that RSA key factored, pretty easily. It only takes enough energy to boil like a teaspoon of water. But when you try to break a 228-bit elliptic curve key, assuming you're not using a quantum computer and you're just using regular computers, right now it would take about all of the energy required to boil off all the water on Earth, so all the oceans, lakes. So it's basically impossible. And the highest broken RSA key is around 800 bits. Highest broken ECC key is around 100 bits. So you can see there's an immediate space advantage to using elliptic curve cryptography versus RSA. So most RSA is keys are around 1024 bits to 4096 bits. I think my private key actually is 4096 bits RSA, but ECC keys can usually range from 192 bits to like 512 as like a super secure guarantee, but usually like 196 to 256 bits is more than enough to be like computationally infeasible, even for like state actors. So, okay, so now we're going to sort of jump a little bit away from cryptography. We're going to actually focus on a cryptographically secure random number generator that uses the properties of elliptic curves to generate cryptographically secure random numbers. Some context before I jump into the algorithm. Cryptographically secure random numbers are hugely important because they're used to generate keys. If you have a broken random number generator, then you can generate keys that are very predictable. And if you generate predictable keys, then people can just snoop your traffic because they can just regenerate your key according to whatever their predictions were. So DEC DRBG was essentially a random number generator that tried to use elliptic curves to say, oh, like I'm generating securely random numbers, because you can't really see how to get to the next point on like an elliptic curve. And we'll go over some of its properties, but there were a lot of problems with dual ECDRBG. Notably, it was very, very slow for a cryptographically secure random number generator, more so than its contemporaries. And more importantly, there's a lot of evidence that it houses what's called a cryptographic backdoor. And I didn't define it there, but a cryptographic backdoor is basically a backdoor that is actually cryptographically secure. So you can't prove it's a backdoor unless you can perform some trapdoor function, which is ultra cool. It's like protecting a backdoor into an algorithm using the properties of the algorithm itself. So, and we'll talk about how they did that. But NIST, being the idiots that they are, standardized it in 2006, mostly because I think the NSA paid them a lot of money, but they actually provided a set of required parameters that were like 2 points on this standardized curve. And these 2 points, they're like, you can't get NIST certified unless you use these 2 points. Like you have to use these 2 points. And it's theorized that these 2 points are actually related in some way, but nobody can prove it because proving that they're related is exponentially hard. It's solving the discrete logarithm problem, which is what we talked about earlier. And yeah, so there were some documents that Snowden leaked that basically said that the NSA created the backdoor, but they didn't release the relationship between the points. So, if you ever work for the NSA, that's, that number, that magic number is probably stored on some file somewhere in the NSA's network. And yeah, so there are a bunch of smart people who actually looked at this. Two blokes from Microsoft, Dan Shamlo and Niels Ferguson, basically in 2010, I think, they were like, oh, like if you look at this dual ECC DRBG random number generator, it's basically broken. And you could choose, if we choose our own P and Q, we can basically recreate the entire state of the pseudo-random number generator using just a few bytes of output. So all they needed was like 32 bytes of output, and they instantly know all of the next random numbers that random number generator will produce. And that is actually a huge problem because in SSL, the first key that's sent is usually a public key, and actually that is generated using a cryptographically secure random number generator. So if you could just snoop the public key, recreate the random number generator, and then use that to predict all private keys, you can basically break any internet traffic. which is why it is a very dangerous algorithm. Anyways, we're going to talk about it. So the basic implementation, fair warning, this is like pretty dense, pretty math heavy, but I'll try and like simplify it as much as possible. So basically, DRBG takes in a curve, which is usually NIST to P56 and 2 points. And it starts off with a seed, like all random number generators. The seed is 256 bytes long, or bits long. Basically, when the user requests output, from the DRBG, there's really two steps. Oh yeah, it's fine.
Switch this.
There are two steps that occur. The first step that occurs is you see there's a state. There's a multiplication. So S1 equals S0, the initial state, times this P point. And then we take the X value and we store it in S1. And then we take another, and we perform another multiplication. We take S1 and we multiply it by Q. And then we just take the X value of that. So S1 becomes S0. So S1 becomes the new state of the RNG. And R1 is basically sent to the user. So R1 is theoretically random. And if we go to the next slide, there's some more stuff, but that's not really relevant for what we're talking about. So this is basically a block diagram of what the random number generator looks like. So you can see S0 to get to X to S1, we just do a multiplication with P, and we take the X coordinate. And then using S1, we produce our first random number, which is taken by just multiplying S1 with Q. And then we take the X coordinate, we chop off a few bits, like 16 bits, and then we give that to the user. And we just keep repeating this process. If the user wants more bytes, they just do another multiply, another 2 multiplies. They get a new state. They, send off this R2 and they store S2 and they keep doing that and so forth. Okay, and now let's talk about how this might be backdoored. So recall earlier that say an attacker knows what R1 is. So R1's public. It's like some public random output that came from this random number generator. So maybe like a public key. And they also know this secret relationship that P actually equals N times Q, where N is a scalar value. Can they reconstruct what the next state of the RNG will be? The answer is yes, they can actually. So basically, R1 equals S1 times Q, and you take the X coordinate. So the first step is to recreate S1 times Q, which is the point on the elliptic curve that R1 corresponds to. So what we do is we guess the top 16 bits, the truncated bits, which is usually a small amount of bits. I think it was, like 16 bits is only like 60,000 possibilities, which is trivial to implement on any modern computer. So then they essentially guess what S1 times Q is. They solve the elliptic curve equation to get the Y value. So now let's say they have S1 times Q. And we want to find the next state, S2, which we can then use to predict all of the other states of the random number generator. So then using our math, using this formula, this relationship, we know that S2 equals S1 times P, and you take the X coordinate. So if we have S1 times Q and P equals N times Q, and we know what N is, then all we have to do is we take S1 times Q, which we guessed earlier, we multiply it by N, and the N multiplies with the Q to get P, so then you end up with S1 times P, which is the same thing as S2. So just by multiplying N with the state we guessed, N being our secret backdoor value, we basically reconstruct the entire DRBG's next state, and we can predict all future output. So this is a pretty nice animation that shows like all of the sort of steps to recreate the DRBG state. Basically, the attacker observes the first random output. They guess what the top 16 bits are, which is like the non-shaded area. So now they have R1, they recreate S1 times Q, and then they multiply that with N, which is our cryptographic backdoor secret. And we end up with S2 now. So now we have S2, and what we can do is as an optional state, or as an optional check, is we can observe the next output, and we can compare it with what we generated. And if they equal, then we've successfully guessed the next state of the DRBG. Otherwise, we can just keep repeating this process until we actually get a correct value for S2, and then we're golden. So you can actually find the actual NIST standardized points that the DRBG uses, or that was supposed to be used with the DRBG. They're in a now redacted, I'm not sure, it's not redacted, but it's a recalled NIST standardized paper. Px and Py are the coordinates for the first point, and Qx and Qy are the coordinates for the second point. Again, they're theorized to be related in some way, but you would have to solve the elliptic curve discrete logarithm problem in order to find out what that relationship is. Yeah, and we were actually gonna do, or we were thinking about doing a DRBG type REPL thing, but it's a bit complicated to input or to recreate. But you know, if you're interested in that sort of stuff, the math is actually, once you have all of the elliptic curve, you know, the elliptic curve framework done, it's actually not too hard to implement the rest of everything else, or the rest of the guessing framework. Yeah.
Awesome. Well, thanks for hanging in there, guys. Do we want to go over the third exercise before we sign out? I don't know how you're doing on time. Should you do it? Should I do it? What's going
on? I think I could go over it. Unless you want to.
Either way, whatever. Like if you are waiting for something else, like if you're late for something, then go ahead, because I can take care of it. But if you want to, I won't take that away from you. I'm checking to see where people are at on that right now, actually. We do have a few submissions on that. I see 4 different submissions, actually. So that's pretty good.
Okay, I mean, I guess I could just go over it quickly, because I think I wrote out the
solution?
The basic, yeah.
Cool. Let's see if we can get the screen sharing to work first try.
Okay. Fingers crossed. Okay, is the screen sharing good?
It's loading. It looks good. Looks good.
Okay. Let me go down here. Okay, so the basic solution is this. So this is what the recursive double and add might look like. Pretty simple. You have if d equals 0. So this is the 0 case. This is like raising, you can imagine this is like raising a number to the power of 0. It just returns 0. So the 0 point is 0, 0, which is not actually guaranteed to be on any elliptic curve, but it's just treated as like the 0 point because it has nice properties. Okay, and if d equals 1, this is like basically raising a number to the power of 1, so it just returns p, the number itself, or in this case, the elliptic curve point. Okay, and then in the odd case, you basically have you do a recursive call where you decrement d by 1, and then you call it on q, and or you say the results in the queue, and then you just add p to q. So this is pretty standard. And then this is the doubling operation, where if the scalar d is even, then we just divide by 2, and then double the result. So nothing too hard. Iterative double and add is also very similar. So this is like the first challenge. In fact, it's actually shorter and faster than the recursive one. Basically, to make this iterative, you just iterate over each bit of d. So like, you look at the last bit of d. If d is 1, then you perform an add, and then you always double, and then you shift d over by 1. And this is basically a direct implementation of the pseudocode. Okay, and then the Montgomery ladder is a bit more tricky, but also still pretty straightforward. Basically, the trick of the Montgomery ladder is you actually have to reverse the number of, or you have to figure out the number of bits in your scalar so that you can process it in reverse order. So in this case, this code here just calculates the number of bits in the scalar kind of inefficiently, but still. And then over here, basically, we just iterate over it backwards. So we start with the most significant bit, and we go all the way to the least significant bit. And then this is the actual ladder itself. So again, just taken from the Wikipedia's pseudocode. But you can see that in here, for each bit, we're performing an add and a double. And no matter what this value is. So even if this is 0 or 1, we have an add and a double here, and an add and a double here. Whereas with the iterative or recursive double and add, if we get an odd case, we have to perform an addition, and then that will reduce it down to the even case. So every odd bit, we have to perform an extra addition, which is not ideal. But yeah, and both of these are obviously can be done in logarithmic time because you're just iterating over bits, basically. And and I guess as a last thing, the actual tests are pretty interesting, but basically this is like the 256 NIST curve. This is actually the dual ECC DRBG point that I ripped from the NIST paper. And this is actually the x coordinate of the second point, and then we just multiply them together. And then and then there's some other tests, but that is basically it.
Awesome. Well, I think that pretty much covers it then. Did you have any last comments before we wrap up here, David?
No, I think I'm good.
All right, sweet. Well, I hear, and hopefully you guys don't hear too, I think there's like a leaf blower coming up outside of my garage. So I'm going to go ahead and sign off pretty quickly here. Also crickets. The crickets are normal. They're my friends. I love the crickets. Nope. We are going to call it here today. I'm going to go ahead and hit the